Welcome back to Engineering Acoustics. Hi, this is Professor Ryan Harne. In this video, we'll generalize our analysis of acoustic source modeling to understand how sound propagates in the near and far field.
So let's get started. We've seen that we can generally model more complex acoustic sources by discretizing the surface into a large number of point sources, but they must be acoustically small, so that they are small with respect to the wavelength, and the point sources must be fairly dense, so that they're spaced apart by less than a sixth of a wavelength. And this is precisely a realization of Huygens Principle. In other words, that every acoustic wavefront is itself the combination of an infinitely large number of infinitesimally small point sources that themselves radiate spherical waves. This modeling principle is directly applied if we wish to analyze the near field. In other words, sound fields only a few wavelengths from the vibrating surfaces. Take, for instance, our generator. We take our superposition of acoustic pressure from the first source and its contribution from R1 and T, the second source and its contribution from R2 and T, and we would continue this for all n sources, so that we could rewrite this more generally as being a sum from the indices I to capital N of the acoustic pressure contributions from source I, radial distance I, and time. In other words, we can then use this technique to analyze how the sound fields add up and either converge or destructively interfere in the near field. In the far field, in other words, when the field point is many wavelengths away from the source surface, we have the same acoustic pressure summation. The total acoustic pressure is equal to the pressure contribution from the first source, the second source, all the way to the nth source. But if we wish to simplify this situation, especially considering the phase relationships in the far field, we need to analyze the interference phenomena that will occur. So considering all of the radial distances, for instance, using the angular notation theta and radial distance r to the field point in an xz coordinate system, when all of the acoustic pressure contributions add up from the multiple point sources, we have a simplified version of this of A on R e to the j omega t minus kr multiplied by the sum from I to n of a phase term e to the minus j k capital D sub I sine theta, where this capital D sub 1 for the R1 case of point source is determined as the dot product between the vector D1 and the vector R. When we use this approach for all of the point sources, what we're effectively identifying are all of the relative spatial or phase differences between these parallel lines from the point source to the field point very far away. So what is very far away? What is the far field? We've mentioned a few types of far field places so far. The first we found was the acoustic far field, when R is much greater than lambda. We are many wavelengths away. And the significance of the acoustic far field is that our specific acoustic impedance goes to rho naught c, so that the energy transfer of the spherical waves is nominally identical to the energy transfer for plane waves. We've also heard of the geometric far field. This is a case where R is much greater than capital D, or D is the characteristic dimension of the overall source. So this is more distant than the source size. The interpretation and significance of the geometric far field is that the beam pattern is now constant. In other words, when we are closer than the geometric far field, radial changes in R would actually fluctuate in the beam pattern, but in the geometric far field, the beam pattern is constant. The final requirement to be legitimately and full-fledged in the far field is a source size factor. This states that the radial location R must be much greater than the ratio of the characteristic dimension squared divided by the wavelength. This assumes and penalizes the case when lambda was small the source size cannot be too small. So for instance, considering certain small acoustic sources that generate very high frequencies, the source size factor takes this discrepancy of acoustic dimension, geometric characteristic dimension, and far field location all into account at once. Our three dimensions of relevance, the wavelength, the radial location, and the characteristic dimension, are all encompassed in the source size factor. All three of these requirements must be met in order for our field point to be in the far field. So let's summarize. When we're near to the source, only a few wavelengths away, the general summation applies, and there's no simplification that can be undertaken. But when we're far from the source, we're able to simplify many of the phase and interference phenomena into a superposition of complex exponentials. We can generally apply either of these cases, whether we're close or far with respect to the source size and wavelength. This modeling technique is a discretized version of what's called Rayleigh's integral. It's named after Lord Rayleigh, who was the 1904 Nobel Prize winner in physics. He also contributed significantly to optics, but he's considered one of the fathers of modern acoustic physics. Rayleigh's integral states that the acoustic pressure is equal to the atmospheric density rho naught multiplied by 1 on 2 pi by an integral over a surface S of the acceleration located at x, y, and z divided by r multiplied by e to the j omega t minus k r prime, the integral ending in ds. So what are all of these values? Let's consider our generator and apply a coordinate system in origin somewhere at the geometric center of the generator. Our radial location field point has values r, v, and theta. The area that's over our integral is S. It's the surface area that radiates sound. We're integrating over this. And if we identify the acceleration at a certain point on the generator, we may even be able to measure this using an accelerometer. We can measure this acceleration and the local radial distance between this acceleration point and the field point is r prime. Now, in general, Rayleigh's integral is extremely difficult to calculate. Only a few special cases can be computed. For instance, radiation from a circular disk, from a square plate, a rectangular plate, a triangular plate, and so on. only nominal geometric objects can really be evaluated in a simplified way by Rayleigh's integral. So in general, we discretize the problem and use our point sourcing method, which is an analog to the direct integrated approach. But this is not a one-size-fits-all modeling approach. Certain sources and frequencies are poorly suited for this discretized modeling of acoustic sources we just described. For instance, interior spaces, and especially small interior spaces. The sound field in these environments is heavily dominated by reflections, for which our approach presumes there are no reflections. Or if the source is outside in a large domain but reflects upon itself. This in fact is quite common, based on the arbitrary shape of certain products, power goods, and so on. This approach is not relevant also when the wavelengths are very small compared to the device size. The computational requirement under this condition would be quite high, and in the specific example of a circuit board, we also would have many reflections in this space. On the other hand, this modeling approach is quite helpful for many sound sources. It depends on meeting the multiple criteria, understanding whether we're in the near or far field, and appropriately discretizing the source to make sure we're small with respect to the wavelength, and our distance between the discretized point sources is also much smaller than the wavelength. So let's summarize what we've learned. So long as reflections and diffractions are not significant, we can model the sound radiation from vibrating surfaces as a discretization of Rayleigh's integral. And this approach is very easily implemented in code, and it works well for both the near and far fields. But we must meet certain requirements regarding the density or distribution of these point sources and their relative size with respect to the wavelength. And the far field is defined by three criteria: the acoustic far field, the geometric far field, and the source size factor. It's essential to meet all of these three criteria in order to measure overall sound levels.
That's it for this video. In the next video, we'll leverage this analytical technique to model the sound radiation from specific distributions of acoustic sources called acoustic arrays.